Okay. Good evening, ladies and gentlemen. Thank you all for coming out tonight to learn about what is soon to be a revolutionary new technology. My name is Andrew Way, and I'm the project manager for a team of engineers and computer scientists here at Memorial University of Newfoundland. And for the past 9 months, we've been working on a project in collaboration with over 80 students from 5 other universities from across the United States. And the project we've been working on is a new form of travel, a new form of connecting the world in cities and traveling between cities. And so the next 45 minutes or so, my job is to explain to each and every one of us exactly what this technology is, how it works, and how it will change the world. This technology is called HyperLoop. So imagine a world where you can travel from across the province from Cornwall to St. John's in about a half hour or so, and a world where you have tubes side by side, potentially by the dozen, stretching from horizon to horizon, with pods effortlessly flowing through them at almost the speed of sound and perhaps beyond. Now, this sounds really like a world of science fiction. I mean, to travel in a tube sort of conjures up images of Futurama or Jetsons, where people traveled through pneumatic tubes. And of course, up until now, this has been a world of science fiction. This has been a world of the impossible. And one man thought of this world, and he also thought it was science fiction, but then he decided that imagination and science fiction simply wasn't a suitable label for this idea and this world. And that man was named Elon Musk. Elon Musk was born in a South African city called Pretoria on June 28, 1971. His mother was May Haldeman, who was a model from Saskatchewan, and his father was an electrochemical engineer who was raised in South Africa. Now, as a child, Elon could always be found with his head buried in books, devouring information at an incredible rate. He was a gifted child, and he was always curious and always imaginative. At the age of 12, he actually designed his own video game called Blastar. And if you go searching online, you can actually find it. People have recreated Elon's game, and it's sort of a weird game. I mean, you have to destroy some sort of enemy with a status beam, which really, no one really knows what that is to this day. But anyways, that's not too bad for a 12-year-old. Now, as he aged, Elon kept his imagination, he kept his creativity, and the dreams that a child would normally have, those dreams that he had did not die as he aged, but rather they reached actualization. They reached realization. They became reality. Now, many people consider Elon Musk to be a real-life Tony Stark. He's a billionaire who's always constantly on the fringes of human technology, trying to extend what it is that people are capable of doing. And Elon's grandfather, Joshua Norman Haldeman, explored Africa with his plane. And you can sort of guess that maybe Elon got his explorative nature from his grandfather. And while Elon doesn't want to explore Africa with a plane, he actually has his eyes set on something much bigger, and that's the exploration of our solar system and the colonization of other worlds. And the ultimate goal, the ultimate thing that's driving him is the preservation of the human species. He knows that in order for the human species to survive any future phases in evolution, he knows that we have to abandon our addiction to fossil fuels, and he knows that we also have to colonize other worlds, because Earth will not last forever. Now, when he created these 3 companies, or helped in the creation, SolarCity, SpaceX, and Tesla, he's helped ensure the survival of the human species. He's transitioned humanity's dependence away from fossil fuels into non-traditional, more renewable energy sources. SolarCity is a company that develops solar panels, so it helps us obtain energy from the sun without having to use or burn fossil fuels. Tesla is a company that manufactures fully electric cars for a multitude of price ranges. And in fact, the Model 3 is actually being released on March 31st for a very modest price of $35,000 US, which is pretty good considering that a price for an electric car was usually quite high up until this point. Now, SpaceX is a company that develops rockets. They have been supplying materials to the International Space Station with their Dragon spacecraft, which was the first ever commercial spacecraft to do so back in 2012. And in 2017, they'll also be doing another first, and that is delivering manned cargo, so people on board with their manned version of the Dragon spacecraft to the International Space Station. And they'll be doing that in 2017, so another first for this company. And this brings us to another idea. Those were the first 3 ideas. This new one is the HyperLoop. And this is something else that Elon now has his eyes set on. It's the development of a technology that allows you to travel up to 1,200 kilometers an hour, be completely unaffected by the conditions of weather. So imagine being able to travel from Corner Brook to St. John's in about 35 minutes, regardless of what time of day it is. You don't have to watch for moose when you're driving. Regardless of whether it's raining or it's sunny or it's snowing, you're basically protected from the elements, and every ride is always going to be the same every time you do it. This is the technology that Elon has created, and he's given it to the world, and it's up to the world to develop it and make it a reality. So we actually have the opportunity to be part of this dream that Elon has. Now, the technology we see is in its infancy. What we're looking at is the unknown. It's a completely foreign thing. The world does not have this technology yet. It's beyond the fringes of what we can do. Now, this idea is in the hands of hundreds of thousands of engineers, scientists, and hobbyists all around the world to try and make this technology a reality. It's up to the world to do with it as they please. Now, this technology is controversial, although many people praising it. There was much opposition to it, but yet at the same time, people still really like the idea. And it's going to be seen in the coming decades who has their feelings justified, whether the Hyperloop becomes a possible technology, and if it's possible, is it feasible? And that's what we're going to find out in the coming years, in the coming decades. Now, to understand the Hyperloop, we're going to approach it using an analogy, a combination of multiple technologies that we're probably all already familiar with. And you can look at the Hyperloop and you can dissect it into 3 different parts. The first is an air hockey table. I mean, most of us have seen an air hockey table, I would think. The second analogy, or the second part of the analogy, is to understand the Hyperloop in terms of a Concorde jet, which was a supersonic jet plane that was retired, I think, a couple decades ago, but we'll still look at how the Hyperloop incorporates technology from that. And the third analogy is, of course, looking at how the Hyperloop is similar to a railgun. Now, a railgun is probably less familiar to most people, and in fact, what it is, it's actually being developed as a new weapon, but we're not interested in the chaotic aspects of the technology. We want to make it a peaceful technology, and so we'll look at how the Hyperloop is similar to a railgun. Now, before we look at why you would ever want to design something like an air hockey table, you have to look at the benefits of doing that. The answer to that question is kind of simple. It's friction. Whenever you're driving your car, the wheels are constantly interacting with the surface upon which the car travels. If you look at the green circles there, these are the atoms of the wheel of the vehicle. And the blue circles are actually the atoms of the surface on which the vehicle travels. When you have a force or a weight that is acting on those atoms, they become intertwined. They interlock with one another. And it's a lot like if you took 2 layers of Velcro and you stuck them together. The 2 layers are made in such a way that they stick together, and if you try to pull them apart, it's kind of difficult. The same thing happens with friction. The atoms intertwine with one another, and it's difficult to take them apart. And this is what slows you down. The reason why you don't see me ever so slightly sliding across the room right now if I sit still is because of friction, because the atoms in my feet are interlocking with the atoms of the floor. Now, this is why we want to have something that's similar to air bearings in a technology. It's to minimize the impact of friction. To avoid having friction with the floor, the surface, we need to be suspended from the floor. We need to not contact the floor, and that's how we avoid friction. And this is why we incorporate air bearings. Essentially what it is, it's a means of levitating your vehicle so that you do not contact with the floor, so that you avoid the nasty incorporation of friction into your vehicle. And so you can look at the diagram on the right here, and you can see there's several of these weird upside-down air hockey tables. And what happens is that the air comes from the air hockey table, so to speak, or the air bearing, much the same way an air hockey table does. And the air is pressurized, and so it builds up underneath the pod, and it ultimately lifts the pod upwards. So the air hockey table, or the air bearings, are responsible for creating a pocket of pressurized air underneath the pod that ultimately levitates the vehicle. And this is what allows you to not contact the surface, but still be able to move freely. Now these here are actually pictures of, or 3D renderings of the skates or the air bearings that we're actually developing right now. So these are the ones that we've designed, and I know that if the students at Northeastern University, which are students also on our team, one of the universities that we're working with, if they heard me constantly referring to their air skates as air hockey tables, I'm sure they would be kind of offended. But they're definitely more than just air hockey tables turned upside down. Now the picture you see on the right is actually a cross-section of the pod. If you took if you cut it widthwise, this is what you would see. And you can see the things circled in red are actually the skates themselves. And so those will be underneath the pod, and that's what the air comes out of to lift the pod upwards. Now you might be wondering, how is it that we can have air that suspends what is potentially thousands of kilograms? I mean, we walk through it, and I'm breathing it right now. There's no resistance and not a problem. If you're walking outside, the wind's not too bad, unless you live in St. John's, where the air is incredibly forceful. And there you kind of have an understanding of how forceful air can be. But the idea is that air has to be of different pressure in order to lift things upwards. And if you look at the picture here, we can have a really simplified diagram of a HyperLoop pod. The circles on the bottom are actually air molecules. And you'll notice that there are less air molecules on the top than there is on the bottom. What does that mean? Well, each air molecule is constantly colliding with the surface of the pod. And if you have more air molecules underneath the pod, basically you have more air molecules constantly colliding with the pod. So the reason why we can lift thousands of kilograms is because there's more air underneath the pod than there's on top. Therefore, you have more air molecules hitting up than you have air molecules hitting it down. And so there's this positive amount of air molecules pushing it upwards that leads to a net force upwards, and it suspends the pod. And it's all great that we can have a mathematical description for how a HyperLoop can be lifted using air, but are we really sure that it works? I mean, sure, on paper everything sounds fine, but once you put it into application and once you try to engineer it, well, it's sort of a different story. But you see, some of the students at Northeastern University, which is the university responsible for developing the air skates, have evidence that proves otherwise. The needle you see in the bottom left is actually showing the oscillations of the air skate. This thing is completely suspended, even with all these bricks on top. It's actually completely isolated and does not contact the floor on which it travels. So like I said, the needle here is actually measuring how much the pod is moving up and down. It's moving up and down pretty quickly. It's oscillating with a really high frequency. So we know it works, which is good. I will try and get back into this. Okay, sorry about that. So we also did another test as well. It's a little more rigorous and a little more controlled. And we've taken into account the presence of people into the pod. And this is the outcome. So we know it works. So further proof that even if you add people into the equation, it still does work. And Milan is quite happy about that. So I always think that if this project doesn't work out and the HyperLoop doesn't work, there's always the possibility we can create hoverboards with this technology. So there are alternatives to air bearings as well. Like, air bearings are an alternative to wheels. There's also another option, that's magnetic levitation. And it's no surprise that maglev has found its way into the HyperLoop, considering the fact that magnetic levitation is something we use today. In fact, the train in Shanghai uses magnetic levitation. It's suspended by using opposing magnetic fields, which lifts it upwards in sort of the same way that air bearings lift a pod upwards. We have a force that exerts the vehicle upwards. But there are, of course, disadvantages and advantages to every form of suspension, but this is also one that's also being considered with the HyperLoop. Now, as a summary, we've seen that by using air bearings, which are sort of like upside-down air hockey tables, we can suspend what could be thousands of kilograms. So we have these things that the air comes out of. It forms a cushion of air which is pressurized, and it exerts a force in the object, lifting it upwards. And this is how we can maintain no contact with the surface on which we travel and go very, very fast. Now, this brings us to the next part. The HyperLoop pod requires the usage of pressurized air, but the question is, where do we get this pressurized air from? And this sort of ties into what we're going to talk about now. Now, the Concorde jet analogy is used for the HyperLoop, and we have to understand why we want to do that, just like how we want to understand why we want to incorporate an idea of a air hockey table into the HyperLoop. Now, there's another problem with friction, and that's the source of aerodynamic drag. And if we had all of us now go out to the lobby and sort of compacted ourselves into a nice little group, and someone tried to squeeze through this group, it's really difficult to do it because there's so many people in the way. But if you space them out evenly, you can very easily navigate through the group. This is the same principle applies to air. If you have air of high pressure or a lot of air molecules in one space, it's difficult to push past it. If you have less air molecules, it's easy to push past it. This is what we can see here. This is the air in front of the vehicle is impeding its motion if there's a lot in front of it. Now, another aspect of aerodynamic drag is if we try to take that same sparse crowd spread out, and we try to run really fast through it, it still becomes difficult because now we have to make sure that we're really agile and not hitting anybody. So there are two main things that's affecting aerodynamic drag, and that is how much air is in front of you and how fast you're going. So how do we fix this problem? How do we overcome aerodynamic drag? Well, the solution is obvious. You remove the air. But if you do that, if you remove all the air from the world, you don't really have much of a world to live in. So to counter that, we have to create our own little world, and that's a tube. And the tube is basically, you take all the air out of it, and you try to take out as much as possible. You might be thinking, though, why not just take all the air out? But there's a problem with that as well. There's cost. See, if you have something that's 500 kilometers long, and it's inevitable that you have leaks in there, so the air is going to find a way in anyways. So we sort of have to accept the fact that we can't have a perfect vacuum, or else we just have to have a lot of air pumps constantly pumping out air. So we just try and get a near vacuum instead. And so this tube has not quite a vacuum, but close to it. But again, there's still other problems. Even if we've taken as much air as we can out of the tube, there's still one significant problem, and it's called the Kantrowitz limit. It basically states that as you move exceedingly fast, there is a point at which the fluid is acting on you so heavily that you have to exert a lot of, or use a lot of energy to try and get past it. You can imagine that with a syringe. If you took a syringe, plugged one end, and pushed the stopper in, at first it's really easy, but as you continue to do so, the air becomes more and more compressed, therefore more and more pressure, and this exerts an even stronger force. Eventually it becomes almost impossible to push it anymore. Same thing applies to the HyperLoop. The faster you go, you'll eventually hit a brick wall where you can't move any faster without having to put in a lot of energy. And this is how we solve this problem. It's an axial compressor. If you've ever looked underneath a jet plane before, and you've seen this exotic looking thing that's not quite a propeller, you're looking at basically a jet engine with an axial compressor. Now, the axial compressor isn't the whole thing. If you look on the picture on the right, the thing on the left is actually an axial compressor. The thing on the right is the chamber where we burn fuel for thrust. So all jet planes really are just rockets, but shaped in a different way. And the job of the axial compressor is to take the air in front of the plane or in front of the axial compressor, compress it, and then use it to inject into the fuel to burn it. And the reason why people do that is so you can have more fuel efficiency and burn more fuel. But with the HyperLoop, we are not burning fuel. In fact, we have a different application for an axial compressor. And that's to take the air in front of the pod that we've just been talking about, remove it from the front, compress it so that we can manage it, and then push it out the back. And that's how we overcome the Kantrowitz limit. Now, it also turns out we can use that pressurized air to supply to the suspension, to the air bearings. So we're killing 3 birds with one piece of turbo machinery. That is removing the Kantrowitz limit, the problems associated with it, adding thrust to the back by taking the air from the front, pushing out the back, and also supplying air to the air bearings for suspension. So 3 things just by incorporating this piece of technology. So we've seen that by adding in this idea of turbo machinery that's used in airplanes, we can overcome the Kantrowitz limit. We can supply pressurized air to the air bearings so we can float. And we can also push air to the back and use it for thrust. Now, this is the most exciting one. This is the railgun analogy. As you can see, it's probably pretty exciting. So the way that it works basically is that you have a projectile, or this is what it's used for in this application for weapons. Basically, you have a projectile that is propelled magnetically. So in a lot of the same way that if you took 2 bar magnets, north poles, put them together, they repel. We know that from experience. Now, the railgun is used in very much the same way. It's basically you have a really, really strong magnetic field that is opposing another magnetic field, and it causes a projectile to be repelled out through a barrel. And in fact, these things are extremely powerful, and the U.S. Navy also thinks so as well. And they potentially will one day replace every single type of weapon on Navy ships today. You have a lot more energy. You don't use propellant. You just use magnetic fields. And the picture on the right, if you're wondering, is the latest U.S. Navy ship. It's a Zumwalt-class destroyer, and they're actually planning on using the railgun on that for the first time. Now, diving a little more technically into the HyperLoop, but sort of hand-waving a lot of details, you see this blade here, which is called the rotor. It sits underneath the HyperLoop. And the thing that you see here with the bronze or orangey parts, that's called the stator. Now, the rotor is attached to the bottom of the HyperLoop, and as the HyperLoop is moving, basically what happens, and there's a lot of other details if you dig under the surface, basically what happens is you use the stators to create a magnetic field. That's magnetic field number 1. And use this magnetic field to create a second magnetic field in the rotor. So every time you pass through these stators, you have these 2 opposing magnetic fields. And this is what repels each other and allows the HyperLoop to be pushed, a lot in the same way that 2 bar magnets repel each other when you take their north poles together. Now, the energy, of course, like I think I might have mentioned it, but the whole HyperLoop is completely solar powered, so we don't have to get energy from burning fossil fuels. We can just put solar panels above on top of the surface of the tube. We get all our energy that way. If you live in sunny California, you can get about 61 megawatts on average. And while the HyperLoop only requires 21 megawatts on average, so that's pretty good. Now, when we're accelerating the pod, we're using those stators and the rotors, all that stuff, and we're using the solar energy to convert to electrical energy, and that's what we use to create the magnetic fields. And then we convert, or then by accelerating the pod, we're creating kinetic energy, bring it back into electrical energy when we decelerate, and then we get some of the energy back that we actually put into the pod initially. Now, as we've seen, take two bar magnets, you put them together, north poles, they repel. And in the HyperLoop, we're replicating that with the rotor and the stator, and these ultimately repel each other. So without going into too much of the details, that's fundamentally how it works. As a summary, now, we've seen that we've combined multiple forms of technology, and it draws on multiple ideas. There's the idea of using an upside-down air hockey table, or a railgun, for example, or a Concorde supersonic jet. And we combine it all together, and we've sort of got this interesting idea, which is, as of right now, just an idea. And the design's been put forward, and the world now has access to it. We can do with it as we want. It's up to us to do with it as we please. Whether or not to make this technology a reality, or to simply keep it in the books of science fiction, or to keep it as an idea and some blueprint gaining dust somewhere. But, maybe if we work hard enough, it will rise like other technologies did, like the airplane or the car before that. Maybe we'll revolutionize the way the world is connected just like those technologies do. Or maybe not. Maybe it will stay a thing of science fiction. That's what we have to find out in the coming years, the coming decades. But maybe it's not so far to reach. Maybe the future isn't so unattainable, that science fiction isn't so fictitious. Well, we at OpenLoop had the same thought. And I hope by the end of this night, you all will too. And this brings us to today. This brings us to the HyperLoop pod competition, the one that SpaceX is hosting right now as we speak, and is ongoing and has been ongoing for the past 9 months. Ever since July of 2015, hundreds of students, hundreds or thousands of students really, hundreds of teams, 700 teams, signed up and answered the call that Elon Musk had put forward to the world, asking people to take this idea and to turn it not just into another idea, but a reality, something that we can use every single day. Now, we at OpenLoop are, like I said, a single group of those explorers, of all the explorers in the world, and we are looking to see and to make this technology a reality. We're looking to try and contribute to an incremental step in the process of innovation to see if we can perhaps give the world a means to beginning the development of this technology. And that's ultimately our job, and that's ultimately our dream. And now I would like to show you exactly what OpenLoop is.
Six universities, 2 countries, 1 mission. Make the HyperLoop concept a reality. More than 100 students from countless academic specialties have come together to fulfill this common goal. Months of work have resulted in a robust pod design, one focused on scalability and advancing the HyperLoop technology as a whole. As we enter the final phase of this competition, the time has come to build our pod. Join us. Do you feel the vibes?
So you're probably wondering at this point, what does MUN have to do with all of this? So I'll go into presentation mode first so you can see that. But MUN is not just the only team a part of OpenLoop. OpenLoop is kind of an interesting team, and we're one of only a couple out of the 700 that decided to go this route. MUN is joined with 5 other universities from all over the US. So we have Northeastern, Princeton, Cornell, Harvard-Mudd, and Michigan join with us. In total, there's about 80 students that range from engineering students, the business students, computer scientists, and alike, from all over the world, different continents, different backgrounds, different futures. So this team came together and decided to split up the project and take it on a different approach than most other schools. So we don't meet face-to-face like this. We meet over Slack, which is an online collaborative site, and Google Hangouts, which makes it all the more challenging. So how did the team form? Thinking about 6 different universities, especially MUN, we're not even part of the same country. A few students were actually at a seminar down in the US last summer, and they made connections. And when this got posted by SpaceX, there was a message on a message board saying, who's interested in this? Oddly enough, a student from MUN happened to be there. And this student answered that call and basically made a Facebook post. And from there, 14 or 15 students came to a meeting and joined this team, having no idea what it was, but just an interest, much like everyone that's here tonight. This team now has split up the roles. So taking on a problem that has such a diverse background and so much technical work needs to be split up so that it's manageable. So our team basically split this into 4 main areas. And that's going to be air supply, which is what MUN is responsible for. The suspension, Cornell and Northeastern take care of. Our controls is Harvard-Mudd. And then we're also looking at our fuselage, which is taken care of by Michigan. To date, we started in about July looking at this concept. And since then, there's been a lot of demanding deadlines. So at this point in the project, we're actually done a final design and kind of optimizing that design and preparing to start building, testing, and procuring materials. So up until now, we've hit a few targets. First being the preliminary design package. And that's where the 700 teams that originally signed up and said, hey, we'd love to be a part of this, submitted what was a top-level design package. Of that 700, I'd say about half of those teams actually made it through. At that point, we worked even harder to make sure that by January, we had a final design package that we were confident in. Because at that point, they selected who would actually be going to Texas and continue forth. So at this point, we had what was now 700 teams reduced to about 125. And then we traveled to Texas. And to be honest, that weekend was probably one of the coolest experiences any of us ever had. We went down there. We actually met our team for the first time. And at this event, there were media outlets such as Discovery Channel, BuzzFeed, and basically anyone you can imagine. Elon Musk himself actually showed up to the event. The teams competed. The level of technical detail was amazing. Everything you saw was innovative, creative, and well done. So at this event, we basically presented to a number of judges for 2 days and did a formal presentation. It was open to the public for an afternoon where 4,000 or 5,000 people came to College Station, Texas to come in and check this out. At the end of this, when everything was said and done, they selected 30 teams. And these 30 teams then get the opportunity to go to California this summer to actually build and test what will be the first ever HyperLoop pods. So this will be a 1-mile test track out in the nice sunny heat in California, and this will be the first time that anyone has ever tested this. Luckily, our design made it through. So what was our first target was to get through design weekend. We made it there. And now we're on to us the most ultimate goal, is proving this technology is real. So now I take you to a little bit about what Andrew's talked about and what we've been doing so far. So on the screen right now you'll see what's a half-removed shell of our pod. Inside has the internal frame of our fuselage, our air supply, our skates, and our controls. Inside this system, we also have emergency braking. Because there's something that's not known, making sure you can control it and that it's safe is of the utmost importance. When we look at our pod, everyone thinks that this is a prototype and it's a competition that's just going to be something you could have in a room. To put it in perspective, our pod is approximately 725 kilograms, 19 feet long, and about 4 feet in diameter, a little bit off circle. When you look at this, our pod is going to cost about $50,000 US just on materials alone. To put it in perspective, some of the teams using maglev range up to $300,000 for these prototypes. That'll travel up to speeds of about 200 miles an hour. So the first part of our system is the structure, and making sure that this is going to be something suitable for the rest of the frame to sit on. Our structure is made out of 6061 aluminum, and has actually been designed so that it's super robust, because any load, and ours is actually designed for a 2,000-pound load inside the pod for cargo, because just like Andrew mentioned, not just people are the intent of these pods. It's also looking at revolutionizing the way we transit cargo from one spot to the other. So with ours, we've actually looked at that approach as well. Given that, the actual deflection of our frame under that load is less than a quarter of an inch. Or a quarter of a millimeter, sorry, not a quarter of an inch. To make sure that we don't have any interference with our skates that are hovering above the tube. The next part is the shell. So the part that kind of isolates what's inside the pod from the tube itself. You'll see here on the screen is some CFD. And what's been done down in Michigan is we've looked at different shell shapes to reduce aerodynamic drag. Like Andrew mentioned, we want to make this as efficient as possible. So between iteration 1 and iteration 2, basically we had a change in the profile on the backside of the pod. In our last iteration change, we added vortex generators. And you'll see the dark blue has actually moved towards the bottom of the pod, representing that the flow separation has become closer to the pod, and it won't have as high of drag. The other part that's really cool about this shell itself is that it's a Nomex honeycomb that's sandwiched between two carbon fiber layers. So what would be 20 feet long, almost 20 feet long and 4 feet in diameter is very lightweight, very robust, and it's actually a porous media, much like many low-pressure aerospace applications. The next part, and the part that's really exciting to me, is the suspension. So like Andrew mentioned, this is the air bearings and the actual makeup of how this works. So you'll see on the screen here that there's two skates. Each skate is about 12 feet long, 1 foot wide, and has a 1 by 1 inch grid of holes. So just like an air hockey table, there are small nozzles on the bottom that release the air underneath and create this air cushion. In these skates, they're in 3 different chambers. So each of the chambers is fed air from our air supply system, which I'll talk about later. You'll also see on the screen 3 disc brakes that are used for controlling our wheels when we land on the track to stop during normal conditions. But towards the middle of the pod, you'll see 2 small tanks. This is actually our emergency air brake supply that can automatically control, grip the track, and actually stop us in the case of total power failure or loss of supply in our main air system. Probably the biggest challenge we've had with the air skates is figuring out exactly how to model it and how to understand what requirements we have for something that's so unproven at this point, given the fact that we're going to be traveling at super high speeds. So over the last couple of months, we spent a great deal of time modeling in different softwares and doing a lot of CFD to try to kind of converge to what our expectation is. Originally, our mass flow requirements for skates were super high and basically limited everything we could do. We couldn't find components that worked for the flow rates. We couldn't find anything that worked. So we refined that, and we've done some ultra-high fidelity CFD and come to a reasonable conclusion now that we can actually proceed forward and prove that what we're doing now actually is possible. And that test that Andrew showed you actually scales up relatively nicely to what we're looking at, considering it was under an atmospheric condition and also stationary, not moving. So that was a good proof for us. So something that's moving 200 miles an hour, and you're not actually going to be in for this test run. So it'll be a test dummy inside. We're not going to be inside it pushing buttons. It's going to be autonomously controlled. Inside the system, you basically have an array of sensors that measure temperature, pressures, velocities, anything you can imagine, along with position control. This is then fed into our state space control system that uses Kalman filtering, which basically makes a guess at what the position should be based on our algorithm, and then takes in the sensory information and corrects it, so it filters out noise and anomalies in the data. It then sends a signal to one of our few control points. So at our skates, we have controls, so we can control how much air we're letting through. We have controls at our brakes, so that we can control the brake supply and emergency brakes. And we also have lateral control, so that our pod is not going askew within the pod, within the tube. So that brings me then to the air supply system. And this is what MUN's been working on now since last July. Initially, as Andrew mentioned, having an axial compressor is something you really want to have to be able to overcome that cantrance limit. At our scale, we don't face that same challenge. And actually developing an axial compressor, which we spent probably 2 months looking into, and retrofitting a jet engine, proved to not be possible once we spoke to some engineers from HyperLoop Technologies down in Texas. They've actually come and said that they're designing a whole new axial compressor just for this project. So off the shelf, for the low pressure environment we have, there is not technology available that can handle this in an efficient manner. So making the choice we did, we're basically modeling now what will be the startup and the finish of an actual Hyperloop pod run. Because for our 1 mile test track, that's basically all you're getting anyways. That would be your actual takeoff in a real scale. So look at our system. It's basically a combination of many known components. So what one might think is funny, the tanks we're using are actually scuba tanks. So anyone that scuba dives, this is legitimately the tanks we're using. We're using industrial regulators, valves, and hosing that we're actually procuring from Atlantic Canada. So the idea here, and this is our piping instrumentation diagram, is we're basically going to have 8 tanks. They're in an array, and they're attached onto our actual frame itself. These tanks are going to store air. The air is stored at 2,000 psi. We want a much lower pressure than that. So in order to do that, we down-regulate the pressure and control it to the skates. So that's through the main 4 lines you'll see coming down through. Once those get down to the skates, it's at a lower pressure, and then we have proportional control valves on our skates that allow the right amount of mass flow through. Off of this main air supply system, we also have controls for our skates, and then independent systems for our emergency brakes and lateral control. So now that I've said that, and we know a little bit about what the design is itself, we're actually at a pretty interesting point in this project, which is starting this week for us. And we're looking at procuring these materials. So just last week, we submitted a revised design package to our SpaceX advisors. And now we're going to be moving on to actually procuring these materials and actually testing and building this here at MUN. So over the next 2 months, we'll be building the entire air supply system. We'll be running function testing, pressure testing, leak testing in the tow tanks in the fluids lab, and ensuring that we have actual control of our system. Once we're done with this test, we're going to actually ship this down to Michigan. Where at Michigan, we'll have the actual shell, the fuselage, and the skates. And we'll integrate the whole system together. And from there, the controls will be added. And we'll look to do vacuum chamber testing and actually go ahead and have this shipped off to California for midsummer. The current competition date now is set for mid-August. So we'll be having a team pretty much down there all summer working on it. We'll meet up there again before, and there are actual, hopefully, some test runs in the actual tube itself. So testing that I mentioned, first test we're planning on running is basically just a proof that we're not going to have a bottleneck in our system, that we can actually get the airflow to the skates, because that's of the utmost importance to ensure that we can get the right levitation above the tube. The next few tests are all focused on proving that we can control what's going on in the system, that we can brake safely, so that there's no leaks in the system, and so that it can hold the pressure. The last test will be done at Michigan and in Harvey Mudd, and it'll be integration testing. So at this point, we've told you about the technology. We've told you about what we're doing here at MUN at a high level. So now we're going to give you kind of a few pieces of information as to how you can get involved or how you can stay up to date on what's going on here. So the first thing is spreading the word. When we did this and went down to Texas, there was not a whole lot of people outside of our family and friends that really knew what we were doing. No one really knew what the concept was or how big this really could be. And to be completely honest, I don't think we understood either until we showed up and the Secretary of Transportation from the US actually came in and spoke and backed this idea. You had guys like Elon Musk fly in for an hour and talk to students in front of thousands of people. You had every media outlet, every sponsor you can imagine down there, all interested in this. So spreading the word is key, because the more people that know, the more great ideas there will be. This is open sourced. So as Andrew said, Elon Musk put this out here, but he's not the one that's in charge of it anymore. There is a company named HyperLoop Tech who is working on it right now, but there's plenty of other opportunities. And they're trying to work, and everyone's trying to work together to kind of get ideas. Even more to put in perspective, the teams that are competing are even willing to help each other out. There's a group on Facebook right now that has representatives from all teams looking to share ideas and trying to help make sure that we test this positively. The next step is corporate sponsorship. So if there's someone you know that might have a connection to valves, might have a need to get involved with this or an interest in getting involved with this, we would love to speak with them. The more support we have locally, internationally, and across all the world really, will help us actually make this come from what was designed to something we can actually test down in Texas in August. Technical assistance. So these areas of Hyperloop itself is kind of unknown. But within that, there's always something that you can relate to, whether it be a hovercraft, similar to the air bearings, a process plant, similar to the air supply system. Any support you can offer, we would love to have it. So please come speak with us. And the last one is apply. So this is kind of aimed towards students and grad students. Right now, we don't have, say, a list of positions that we're looking for, but we are looking for assistance with sponsorship and also some technical assistance from people that have had work terms or working on, say, their graduate or undergraduate degree at a senior level and trying to actually help us build this pod. So expertise is something we're looking for. If you are interested, you can take a resume and submit it to one of us, or on the next slide here, or you can see it as well, you can actually email that to me. And we have business cards down here. You can get one from us after if you're interested in that. So basically, in conclusion, we hope that you've come here this evening with an open mind, thinking that this is something that could change the world. If you look back years ago when the first airplane was created, it was the same thing. No one knew what was going to happen. Might have seemed like a crazy idea, but look where we are today. So this is the same kind of thing. Just 9 months ago, no one knew what this was. No one believed in this, but look where we are now. We've got hundreds of thousands of dollars, millions of dollars being spent, invested in this, and we've got a lot of international support. So stay interested, stay tuned, and on March 31st, we're actually going to be featured as the Engineering Lecture Series speaker. So 7:30 that evening, come out and check out some more information. Thank you very much.
So for the next 10 or 15 minutes or so, we can take some questions if you guys have any thoughts or suggestions or anything at all. If you want to put stuff in. Yeah. On our team here at MUN, there's about 20 students. So we have mostly mechanical engineers, a number of computer science students, and myself, I'm a physics major. I'm the only one on the team. And we also have process engineer, computer engineer, a couple of them. So about 20 students or so.
How many people consider your team?
On the entire team, there's
about 80.
Yeah, there's about 80 other students, I believe, in the other 5 universities.
This might be a bit too technical, but why did you choose the air braces over the magnetics?
Oh, yeah, that's a good question, and that's a question that we've actually thoroughly thought of prior to going to Design Week in Texas, because we knew that the question was going to be asked, or at least we assumed it was going to be. And the reason being is it's going back to how you want to overcome the Kanchowitz limit and the fact that you need an axial compressor to overcome that. And so if you went magnetic levitation, say, let's assume that you did that, you're not overcoming the Kanchowitz limit just by using magnetic levitation alone. So it's inevitable that you have to incorporate an axial compressor. So if an axial compressor is already in your system, you might as well use the pressurized air from it and supply it to the air bearings. Otherwise, if you went maglev, you'd have to have both maglev and an axial compressor. So 2 systems, twice the complexity, more price. So you might as well just use a simpler system that's with an axial compressor.
How many people can fit in your pod? And is there a trade-off between the number of people that you can fit in each one and, I guess, how fast you can go?
So with the pod design right now, it's basically based on the functionality. So there's no interior design for this pod for this competition. But on a full scale, they're nominally saying about 30 people a pod is kind of what they're looking at. We've actually tailored ours to be more in line with the cargo option, just because the front of our actual cone, our shell itself, is removable. So that can actually slide off, and we can slide cargo directly in. We don't have any of our system within the pod itself, which is a nice feature. We have our air supply system and skates actually embedded in that substructure frame I showed. So there's actually nothing inside. It'll be empty. So when we go down there, we'll actually sit one test dummy inside, and they'll have all sorts of sensors and stuff hooked up to him to see how our ride is. But for this competition, there isn't kind of a quantitative analysis for the interior of the pod.
Building on that, but I would like to ask, what do you think are challenges for your team at this point? Maybe in the future, what do you expect will be the challenges?
One particular challenge, and it's been a challenge for ever since we began. I mean, if you're working with a team of this nature where you have 6 universities that are separated by thousands of kilometers, collaboration, I mean, you'd assume it to be an extremely difficult thing. And it definitely is more difficult than just having all students working in one particular place. Thankfully, because of the internet, I mean, communication is obviously much more easier. But again, knowing exactly what's going on at each university is a challenge, and it will always continue to be a challenge because you can't, physically be there.
And like he's talking about that there, we use Slack. So I don't know if many people know what Slack is, but it's kind of like a guided instant messaging. So you have a different channel that might be called, say, air supply. And to put it in perspective how much we use this, there's actually a 10,000 message limit. And we overcame that 10,000 message limit 3 or 4 months ago. So this is used on a daily. We actually wrote one exam last semester. It was an hour and a half. And when I came out, there was 300 messages in that one channel. So saying that it's hard to keep up on this and to kind of integrate real well is difficult. That's why we've actually developed an integration team now, so that what one team is doing, the other team finds out, so we don't have these problems going down the road. I think the biggest challenge we're going to see going forward now is some of the manufacturing we have. We're in works right now with a few companies down in the States to actually do some of our tight tolerance manufacturing, because like I mentioned, the actual deflection on that frame has been minimal, or it's going to contact the actual tube itself, because we're hovering at 3 millimeters. I know it sounds crazy, but the hover gap is 3 millimeters on that. So we don't want to see deflection. Because if we see deflection, we'll have the frame itself touch the tube versus the wheels that are 3 millimeters above it.
Have the air bearing team looked at a lot of other air bearing products? I guess because I've seen on my own people using air bearings for heavy lift, just for vulcanized roof basement, missing.
I'm not entirely sure if they've gained any inspiration from pre-existing air bearings. I'm sure they have, definitely. But what specific types they were looking at, I'm not entirely sure.
They've looked at different analogies to, like, saying you had a skirted design on a hovercraft, and different shapes of our skates, and different analogies that you have mentioned. I've seen videos exactly what you're saying. I think some of the biggest drivers, though, with the skirt, which is nice for us because it actually would keep the air under the bearing better, is that we don't have room to have that skirt, because then our skirt's going to be touching the tube, and we don't want that. We don't want any of our materials contacting, especially at those speeds. But there has been a lot of time and thought put into the actual design and trying to optimize that cushion from shearing away, moving at high velocities. So roll during turns. Basically what happens inside that track, or inside the tube, there's a track. So we have lateral control on the front and rear of our pod, which will guide its actual motion, so that it'll just activate based on our control system. There's sensory lasers that will adjust our position and send that back to the control system. So if we're a little bit off-centered, or we're going around a turn, one piston will actuate to keep it to the track.
How do you power the initial thrust of the pod?
Powering the initial thrust of the pod, there's actually a pusher being incorporated into the tube. The 1 mile track that SpaceX is fabricating right now, or at least the company is contracted to fabricate. So there's a pusher that attaches onto the rear of the pod and it actually pushes it and accelerates it. And so then you have I should have mentioned, by the way, the linear induction motors that I was talking about, that's using the full scale, they won't be in the test track. So you basically get accelerated by this pusher for the first little while, you coast, and then you decelerate.
I know you guys said you were more thinking paragraph, but when it becomes a passenger kind of vehicle, have you thought of the volume of the thing? Because if you're thinking you're pushing that much air, I would think it would be similar to a plane, but you're in a closed space. So I wonder, if you guys thought about that at all.
So just let me understand your question. You just say,
So you're pushing that much air
Yep.
in a closed space, so the volume is going to be.
it is, and that was the other reason we did not use it for our scale, because taking that air in front, unless you compress it all the air at once, you do have a large bypass duct within. So for us, we obviously opted away from that design. But when we looked at it, I think using a GE jet engine, there was a 6-to-1 bypass ratio, and our actual duct inside, so it took all the air from in front, actually still took up probably what was about a third of the inside of our pod because of that sheer volume you're mentioning. At a larger scale, that is why they're designing their own turbofan. So basically a fan that passes the air back to a compressor and the rest through a bypass system. So that can be routed through, say, either the floor or below where ours is to, or overhead, so that air is passing through and not through the actual pod itself, so that it doesn't obstruct. One cool thing that they are mentioning about their design and what they're planning on doing is if you think about it, driving in a car, if you were going through a city going, say, 100 kilometers an hour, you shouldn't be going that fast. But if you were going really fast with objects close on either side, you looked out the window, you're going to get sick. So one thing people always ask us is, how are you going to be in this pod and not feel either claustrophobic because there's no windows, or not get sick because you're looking outside? So one thing they've actually looked at is actually projecting the outside inside at a more reasonable transition pace, so you get that feeling that you're actually looking out the windows without actually having to see the speed of that, which is something that's pretty cool that I thought you might like.
You mentioned there's the space it might not be, I guess, the scope of your project right now, but if you expand the track over a longer distance, I guess, let's say you mentioned St. John's to Corner Road, there's inclines and declines. So is that something I guess?
So for our actual competition, the track itself is just a straight track, no inclines, no declines. The actual scope of the project, though, in general, will account for something like that. That isn't something we've done a whole lot of work with, but that is something the controls team at Harvey Mudd is looking into, because Princeton themselves are doing a full scalability analysis of what we're doing right now. So taking what we've designed and saying, how can we scale this up? So that's a question that they're answering right now, as to say, it's part of our control system and how we actually adjust. So as we're going up the hill, you're going to need more air supply at the front. That's not something for our competition that we will be incorporating, but it is something for the scalability portion that we will be addressing.
If you put the Hyperloop between San Francisco and Los Angeles, which is sort of the example that people are using as sort of a case study, I think it works out to be around $35 or so per person.
Yeah.
And so that sort of price model would only really work between high traffic areas like San Francisco and Los Angeles. If you wanted to put it, between Cornerbrook and St. John's, I think it's safe to say there just isn't enough traffic between the two cities to justify billions of dollars spent on a Hyperloop. Yeah. So $35 between high traffic cities seems to be the price they're going for.
They've actually designed this with the intent of not having, say, like a huge passenger jet plane where you have, say, 300 or 400 people. They're going to stick to these smaller pods that go very frequently. There's actually one report released said that they hope to send pods like every couple of minutes. So it'd just be basically like a subway station. You'd get on, you'd go, shoot down the track, and then another couple minutes later there'd be another pod come behind. So that it can replace what would be a gridlock in many cities, right? You're not going to be waiting to get on it, and you're not going to be waiting while you're in it. So the fact that they're actually looking at pricing it somewhere that's actually economic is something that makes it even cooler, because $35 to go all that distance, when it costs $35 to get a ride from Mount Pearl to St. John's, is pretty cool. So for our design, based on the weight, so someone asked earlier about how does the weight affect the design at a number of people. So that does affect it. That pusher that Andrew described basically gave us like a range. If you're in a certain weight range, they've nominally said you'll get this certain acceleration. So for our design, the maximum speed is about 210 miles an hour. We've designed to 200 miles an hour. So 200 is kind of our target exiting the pusher. Full scale, though, it's about 1,200 kilometers an hour, so just below speed of sound.
I know this is not part of your analysis for the competition, but have you taken into account the outer shell would be open?
I think we might have, I think we talked about it in the beginning months of the competition. And there was the idea, I think, being thrown around of like it's called the Falcon door, which is something that Tesla, I think, uses in some of their cars or something. Some people, think that'd be a cool idea to have the doors sort of open up like this. People would come out, and then you'd have the part of the station where the Hyperloop rests. You would rotate, and then you basically send the Hyperloop on its way again. I think the problem, though, with these Falcon doors is that you can't simply pressurize a vessel and have an exotic door like that. But most generally speaking, I think the idea is to sort of have this part of the station that rotates and then allows the pod to travel through another tube.
Yeah, so with the actual tube itself, it's going to be segmented. So I think what you might have been asking is, like, once we come through to a station, you're going to be at atmosphere. You don't want an atmospheric pressure the whole tube. So you'll have something that will close off within the tube, and then you just repressurize, or depressurize, I should say, that last section that you pass through. That's kind of the intent. It's the same thing under a failure mode. If there was to be a leak detected in the tube or some sort of anomaly, there's going to be a way that they can actually isolate sections and then work on that section.
So would this be a closed loop, or is this only one way? And then
Both ways, yeah.
Both ways. It's actually stacked, so you'd have two tubes on top of each other. It's the kind of design they've been going with for most of their proposals so far.
You guys look into the tolerance of how much air you have and still keep the
So that's been probably, since we made the decision on compressor, turbofan tanks, once we got through there, that's been what we've spent a lot of our time on and done a lot of modeling to prove. So we're comfortable now that what we have is very robust, because we actually designed our requirement right now based on our latest CFDs, 0.5 kilogram per second of air over the whole skate surface. Our analysis we did for 0.7 kilograms per second of air, and that also has a safety factor of 2 for the time length we can supply that, with actually a little bit of oversupply. So right now we're pretty conservative on that, because it's such an uncertain part of our design. And if it comes out to be in the end that it is really conservative, we might just hover at 4 millimeters versus 3 millimeters. That is why the testing we're doing and Northeastern's doing is going to be really important. One, for us to prove we can get that mass flow through our system without bottlenecking, and two, so that they can prove that under the shear effects they'd see in a vacuum chamber with something moving underneath it, that we can actually keep that cushion.
We did have to account for the size of a dummy, which is about, I think it's 6 feet
Yes.
tall, 80 kilograms or something like that. So, you know, we have more than enough space within the pod, and the dummy can definitely fit into the pod.
I was wondering more like for traveling at that speed.
Oh, you mean passenger comfort when you're
Yep.
traveling at 1,200 kilometers an hour?
Yep.
Yeah, that's definitely one of the biggest concerns with the HyperLoop. Many people think that, you know, you're going 1,200 kilometers an hour, every single little deviation is going to be felt pretty significantly. And so a big challenge with the HyperLoop that needs to be addressed is, of course, ensuring a stable and smooth ride when you're traveling even at those high velocities.
Yeah, so the actual pusher itself accounts for that, so you wouldn't see any more of a G-force on the acceleration part than an airplane would, so you wouldn't feel anything more than that. On deceleration, we've actually designed our brakes so you won't see more than the G-force than an airplane would either when you land. We could just haul on the brakes and it would try to lock up shut, and yes, that would be terribly uncomfortable for anyone inside. But we've actually looked at that and done our time profile so that it's more of a smoother transition.
the manual trains have caused many accidents. So how are you, which are almost at half of speed of what you are saying? So how are you going to handle safety?
Handle the
Safety, yeah.
concerns at high velocities, you say?
Yeah, like in HyperLoop. So how is HyperLoop addressing the safety concerns?
Do you want to answer me?
Sure, go ahead.
So I guess for our system itself, like internally what we're doing, we're basically making sure that regardless of what happens to our pod, so whether we lose power, whether we lose air supply, whether a regulator line spews open, no matter what happens, there's redundancy everywhere. So that if the power loses it, our emergency brakes, the actual air cushion will deplete. You'll drop your 3 millimeters onto the